Okay, finally we can start. And sorry for such kind of delay. And yeah, I hope that okay. I hope everything is okay. And let's talk about today. Let's talk about this hybrid and classic computing to solve the optimization and the machine learning problem for future networking. And this work is done by together with Professor Fan and our 3 joint students, and thanks to National Science Foundation. Okay, and here's the motivation outline. First, we have the motivation for quantum computing. Then, among all the different techniques, we work on this quantum annealing, and specifically, we talk about a specific algorithm called QUBO. And then, okay, by using QUBO, we try to employ into the Bender's decomposition. So the Bender decomposition is a very powerful tool to solve the mixed integer programming. And then we propose our quantum and classic computing Bender decomposition algorithm. And finally, we have the 3 different applications in wireless networking, machine learning, and the smart grid. And we have the conclusion next at the end. Okay. And since starting from 1980s, okay, people can think about whether or not the quantum can be used as a computer. And the Feynman, which is a very famous quantum physics, say, okay, maybe we can use a quantum machine in our computing. But many years later, okay, we have a different company like IBM, D-Wave, and Microsoft that begin to build the quantum computers. So what's wrong with the classic computing? For the classic computing, okay, what's the problem is that, okay, if you have 2-bit, okay, then, okay, you only have 4 combinations to search for integral programming. And if you have more bit, the searching space become bigger and bigger. And then, okay, if you have a 64-bit, just like this chess board, okay, how many kind of combination you need? Probably more than all the elements of the universe. So there's no way, even though it's only 64-bit, there's no way you can calculating for this one. And then one potential plan is to using the quantum. And the quantum, instead of enumerate all these combinations, they can compute parallelly over this 64-bit. So in this case, okay, they can handle very big problem. And then we can have the life science, for example, all these kind of DNA or this protein, how they wrap, how they communicate each other. That is a very complicated problem. And the manufacture and the lodging, and for this kind of, for example, Amazon. 4 of my students after graduation, they went to Amazon. And then they need a lot of kind of constraint about the logistic and the manufacture to reduce the cost. So that's indeed a kind of a very kind of difficult optimization problem. And finally, financial service. So nowadays, okay, and when you go to the when you invest in Wall Street, very few people, okay, will probably, most of them are designed by algorithms. So you are investing against a machine. So basically that is the current situation. And then, okay, for quantum computing, so quantum computing can create a vast number of multi-dimensional space to deal with a large problem. For example, okay, and translate it back to what we can use. So at the beginning, okay, in the first stage, they can activate the spread. For example, in this case, maybe 32-bit. And then, okay, they encode the problem. So the so-called encode problem is that, okay, for our optimization problem, later I will show you the example. By using some kind of model, we can make the optimal solution more likely. And then this is the second step. And then the third step is unleash the power. So basically, okay, try to sample it. For the quantum, as we know that, okay, before you sample it, it can be any state, just like the cat. Okay, the cat can be live or dead, can be any state. But when you unleash the power, when you try to sample it, the one with a very high probability, which is probably the optimal solution, will jump out. And then in this case, you get a solution immediately, even though that, okay, it's with high probability you get that, but the probability is indeed very high. And so in this case, okay, we can solve the problem which classical computer cannot do. For example, for the example I showed you previously, for 64-bit, you need to, classical computer, you need to enumerate 2 to the 64-bit. But for this kind of, quantum computing, you only have 64-bit, and you encode it, and then you sample it, you get the optimal solution. So that's the reason, okay, the quantum computing, if it's implemented, okay, with a large number of bits, and it will dominate the computing society. So that's a great thing. Okay, motivated by this one, okay, there are so many kind of companies nowadays, and it's probably, my understanding, okay, probably become the next hot topic, next big wave after the machine learning. Okay, so that's a kind of a situation now. And also, okay, the global market for the quantum computing is growing exponentially. So typically for quantum computing, you have 3 different types. The first one type is the quantum annealing. So basically, okay, this is D-Wave company. The major application is try to do the constraint optimization. And the general is very restricted to a specific problem. But in this talk, we concentrate on this part. The second part is called analog quantum. So the application is chemical sampling, quantum dynamic, and it can fit more kind of application result. And the third time is a very universal quantum, basically, okay, quantum circuit or something. It can beat all these kind of current RSA algorithm for security, for cryptography, and also kind of, so the generality is very high. However, they have the trade-off. The trade-off is that, okay, for the first type, you can have up to 5,000 quantum bit, and which is very powerful, but it's limited in a certain applications. And for the other type, okay, the more general you have, the less bits you have. So in this case, okay, there's a trade-off. Depending on your problem, you have to use the right one. And currently in your group, we concentrate on the first type for the D-Wave quantum annealing. And we are also working toward to understanding the other type. So here, okay, again, we have 3 different types. This is a gate model, analog counting model. This is third type and the second type, and we concentrate on the quantum annealing. So now let's go to this quantum annealing. So what is annealing? Annealing is that, okay, in the old time, okay, we all these blacksmiths take the sword, heat it into a very kind of hot fire, and after that try to heat it. So that, okay, so that, okay, it will, the metal will be in a better shape. It's a more kind of durable. And for the simulated annealing, okay, for example, okay, if we use on the lower example, and we can show that, okay, and starting from this, if we have the gradient descendant, because the shape of here is not the shape of here is not kind of this figure. They have the multiple local optimal. So in this case, you might either fall into the left optimal or right optimal, left hole or right hole. So in this case, you need a simulated annealing, such that, okay, you try to, it's a heuristic algorithm, is try to push this local optimal up over this small hill so that you can go to the better optimality. And so this is a kind of, simulated annealing. And this is works by the traditional kind of computer. But for the quantum annealing, so basically, okay, at the quantum state, okay, you can be either the left or the right optimal, local optimal. And then they have the quantum tunneling. And then they can, before you sample it, the solution can exist either the left local optimal or right local optimal. However, when you're sampling, the one with a better solution, more minimum on the right one, will have the higher probability to get sampled. So in this case, you can calculate this quantum annealing, in a different perspective. Okay, here is the quantum annealing. And you see this is a very non-convex solution. You have multiple kind of local optimal. And for the circle which is stuck in the non-optimal local optimal, they can use a quantum tunneling to jump from one classic state to another classic state. So in this case, okay, the width of energy barrier is important, but the height is not. So in other words, okay, for this right curve, this is a difficult. This is a kind of for the right curve is the path for the simulated annealing by traditional computer, and this one will take a kind. I mean, the height is very important because you need to heat it up and going up, and then jump to the new local optimal. However, for quantum computing, it can directly jump from the left left local optimal to the global optimal, and then okay, this is a story of the quantum annealing. And then okay, from the energy domain from Q wave, okay, so basically okay, they have the following step. They have the high energy and the low energy, and then okay, at the beginning they have the initial qubit. And so basically, okay, they are not yet coupled, and it can be 0 and 1. And then, okay, and then after that, the qubits are entangled, and which represent this left local optimal and right local optimal. And then if you have more bit, I can have more kind of solution. Here we only have one bit, so I can only show one solution. And then after that, okay, by using certain kind of constraint and put into the circuit, we can make the left and the right curve which fit your kind of function. So in this case, you can see that okay, on the figure C, okay, the 0 part have the higher energy and the 1 part have the lower energy. And with the lower energy, it will have a higher probability to get sampled. And in this case, when we sampled, it's more likely that we sample on the right, more local, more global, global minimum. So this is basically kind of a quantum annealing concept. And in mathematics, they use the Ising model. So the so-called Ising model is this kind of can be represented in this way. On the right-hand side, the first equation, the first component in the first equation is a spin interaction with the applied field. So basically, spin reaction according to himself. And on the second term, we is basically spin interaction with the near neighbors. So this is the case. And here we try to using this kind of for quantum computing, we use a quadratic unconstrained binary optimization. So basically, okay, the objective function is look like this one. So the first term, again, the first term is basically okay objective function, and the second term, okay, for the neighboring, we can quantify this one as a constraint, so that okay, for this QUPO and this kind of optimization problem in this proposed by the D-Wave for the quantum annealing algorithm, we can use such kind of objective function to solve many kind of integral optimization and with a constraint. And here xi is this kind of binary or integral kind of a component. And then okay, you can see that okay, for this quantum annealing is very good to solve the integral programming, like the knapsack problem, assignment problem, task allocation problem, and so on. So for such kind of integral programming is typically NP hard. That is a major bottleneck for this kind of practical mixed integral programming problem. Okay, and then okay, specifically for D-Wave, they have this kind of Hamilton at this first equation. They have the initial Hamilton basically when they kind of have higher energy, and then finally they gradually shrink down to this kind of shrink down to this kind of final Hamilton. On the right lower figure, and you can see the right curve is this kind of the second term, and this kind of the blue curve is this kind of first one. And okay, so the goal is trying to minimize this kind of sigma, which have the binary +1 and -1, and provide subject to provide this Jij and Hi component. For this HI component is basically your objective function, and the Jij is basically related to the constraint. Later, I will show you how to quantify it. In other words, quantum optimization is merely a function of your Jij, which is a constraint, and HI, which is your objective function. So for the basically, okay. We can, for classical, it's much easier to reason that the quantum, for this quantum Hamilton and the quantum effect used internally to work towards the goal. So basically by using this one, okay, we can solve this constrained integral programming. And so basically, okay, also, okay, such kind of thing can map into this kind of D-wave camera graph, so that, okay, they can implement such kind of equations. Okay, so let's give you the example for this kind of, this kind of, Hamilton. Okay, so here the first equation is the final Hamilton, and this sigma can be plus or minus 1, yes or no, okay. And then, okay, for objective function, HI, if we set the HI equal to -5, then okay, and this HI delta is equal to +1. So basically mean, okay, if I have, because we are doing this kind of minimization, so if we have HI means want to have a lower value, then that means we want this one to be true. And if it's 0, it means I don't care. And then it's positive means I want to be false. So by designing this HI, we can design our objective function to tell, okay, what type of things we want to prefer. Okay. Okay. And then, okay, we can, in addition, so this is the previous slide is objective function, and now we come to this kind of constraint. So basically by design the constraint, that means, okay, if the J, if it's more negative, J is more negative, then that means the sigma J and sigma I and sigma J, I want it to be more equal. If it's 0, that means I don't care. If positive, I want them to be different. So by adding this one, adding this constraint, you can see on the right-hand side, if I have 2 bits of a qubit, and then I can describe this kind of, a non-convex kind of a function look like this shape. Okay, so in this case, we have a 2 local optimal. So in other words, okay, we can using this kind of the first equation to describe the constraint optimization for integral programming with any kind of shape, as long as you have a sufficient bit. So in this case, okay, you have an arbitrary shape, and then I can using this method to describe your kind of objective function and the constraint. And after that, okay, when we do the sample, the one with the lowest energy will appear with the highest probability. So in this case, we can do the quantum annealing, try to find the optimal solution in one shot. Okay. So this is the QUBO, and which basically proposed by this D-wave. And what our research is that, okay, for this for integral programming is a important part, but in networking, the most kind of complicated, the most common problem is a misintegral programming. So how could we using QUBO to solve this integral programming? And also this due to the limited bit of quantum computing, we cannot use quantum computing to solve all the problems. So could we using the classic CPU-based computing, such as, okay, we still can solve the problem? And then this is our research that we propose as a hybrid bundle decomposition by using both quantum and the classic CPU computer. So let's think about the misintegral programming. So here we have an optimization problem with X, with a variable of X and Y. And here, suppose we make it simple as a linear objective function with a linear constraint where X is integral, Y is continuous. And this problem is typically NP-hard So basically, okay, it's a very difficult, when the dimension become large, it is very difficult for you to solve using this kind of classic computer. And you will face such kind of optimization problem in many kind of engineering problem as well as big data problem. So then what we can do? Okay, the Bender's decomposition is trying to decouple this mixed integral programming into the pure integral programming and the pure continuous optimization. So in this case, if we can decouple the mixed integral programming into these two sub-problems, then we can solve this kind of pure integral programming by by quantum computing and solving this kind of continuous problem by using the CPU. So on the first kind of equation on the left hand side is the original problem, and then we can replace the HTY, H transpose Y as a Z lower bound. Lower bound. That means with a fix of X, then Y should be a certain solution. So in this case, we solve this one. And then after that, okay, by fixing X in the lower part, by fixing X, the integral part, we try to use the classic computer to solve Y. So in this case, we try to solve this Y problem. And also, okay, by using this kind of linear programming duality, we can propose this kind of feasibility region for this. And then we try to continue, and then, okay, when we continue, okay, when we try to come to solve this kind of original kind of integral program again, okay, and then, sorry, let me come back a little bit. And in this case, okay, this integral part and the continuous part can be solved alternatively. So this is a typically called block coordinate descent. However, these two problems sound to be more kind of independent, even coupled. But the key question is that, okay, could we use this kind of CPU-based second problem to facilitate the first problem? So here, okay, we have when we try to solve the second problem, the second round of the master problem, and the first round, okay, the first round kind of continuous optimization will provide this kind of additional kind of constraint, and this constraint basically tell, okay, your solution is either this kind of in the extreme point or the extreme rate. So in this case, okay, the original problem and okay, the original problem will have the additional constraint for this. So in this case, okay, and then okay, the prime problem with optimization of integral part become in the second round become this one. So you can see that, okay, and compared with the first round, they add some kind of feasibility region constraint. So in this case, okay, the searching space for the second round of prime problem for the integral programming has been significantly reduced due to this kind of the first round continuous optimization. And then, okay, these two iteration is iteratively until it's converged. For the master problem, it will have the integral programming and on the left hand side, and basically you can be solved by the QUBO quantum annealing. On the right hand side is a continuous optimization, which is a sub-problem and which is a kind of can be easily solved by this kind of CPU-based problem, CPU-based computers by using the convex optimization. And then every time the sub-problem is solved, it provides additional feasible region constraint to the master problem. So the master problem, master integral program feasible range becomes smaller and smaller, and so that it can be, finally it will converge. So this is a basic story for Bender decomposition. And here is the algorithm. And so basically, we have the master problem, and then this sub problem. And here we want to put this kind of master problem into the QUBO, quantum computing, and the sub problem into the classic computer. So here, for this master problem, okay. So at least the master problem here again, and for the QUBO, we have this kind of this objective function, and on this Q, on the lower equation. And in the first term on the right-hand side, this is XQJIX. This is basically related to this objective function. And in the second term, that's two sigma term. And this is basically like a constraint. Okay. All right. And then, okay, there's one more problem. If you look at closely at the classic Bender decomposition, between them there's a T. This T is a kind of continuous variable between to link between this kind of master problem and this sub problem. So the master problem, as a matter of fact, is still a mixed integral programming. So this T is a continuous variable. So in this case, we try to quantize this T with a kind of ambit. I mean, and so in this case, okay, the lower equation is try to quantize this T case. So after quantization, the whole master problem become a kind of integral program. Okay, and then we have this kind of classic Bender decomposition on the left-hand side, and then on the right-hand side for the slave problem is a pure kind of classic Bender decomposition on the left-hand master problem is still a mixed integral programming after quantization. On the right-hand side, this is a quantum solvable pure integral programming, and then we can use this QUBO to be employed here. So here again, on the left-hand side is this kind of objective function, and then on the right table we show you that okay, for those type of constraint, and we can using this equivalent penalty to put the constraint into the objective function, and then by using this one, the objective we can write the objective function look like this one, and then we can put this put the different constraint in as according to this table, and then we put a different constraint into this kind of objective function. And finally, this is the whole whole picture. On the right hand side, this equation we have this kind of QUBO, and for the first two items. For the first line is this kind of objective function. For the second line is this T, continuous variable. For the third line, the fourth line is the constraint. And then by using this QUBO, we solve this QUBO in the quantum computing. Well, for the sub problem, we solve for the sub problem, which is a pure continuous optimization, we put into the classic CPU. So here is the overall algorithm, and then this is a kind of basically repeating what I have done. And here is some kind of a simple kind of illustration with a certain constraint. And we can see that, okay, on the right animation, we can see on the left animation, we have this Bender cut. So each cut, we will have a feasible set become smaller and smaller. And on the right figure is the upper bound and the lower bound for this kind of, Bender iteration. And within only 4 iterations, okay, such problem converge. So you can see that, okay, by using the joint quantum computing and classic CPU and modify the hybrid kind of Bender decomposition, we can solve this kind of mixed integral programming and efficient way. So this is the case. And finally, we have this kind of different application. So the first one is the optimization problem in wireless network. And then the first one is the network function virtualization. So nowadays, okay, when you try to, call somebody or download something, you will talk to your access point, like the Wi-Fi access point or base station, and then after that, they have backhaul to connect to the internet. So all this one is fixed out, and basically, okay, is also provided by a certain service provider like Verizon, AT&T, etc. However, in the future, okay, the situation might change. So basically, you have this kind of the different people can provide the different kind of people can for example, I can build a base station in my backyard and try to serve all these kind of my neighbors. And if AT&T want to buy the service, I can sell to them. If Verizon want to buy a service, I want to buy them. So all these kind of, service storage, networking, computing component is not belong to a certain company, service provider company. Instead, they can provide, different company can provide such kind of service. And then finally, okay, the service provider will search the resources so that they can implement certain goal. So in this case, okay, it must be a very large optimization problem. And specifically, we concentrate on example, and then we have the different virtual machine, and then they have the dependence graph on which one have to link finish earlier than the other. So basically, okay, we have virtual machine 1, 2, 3, and then they need a scheduling about the different tasks. So you can see that, okay, we have the time slot, which is a kind of integer, and then we try to allocate them into this one. It must be a very kind of assignment. It's a very complicated assignment problem. And then we have this kind of integer linear programming problem. And then this is a different definition. We have the optimization with a certain minimize the delay, overall delay to finish all these tasks. With all this finishing time and kind of virtual machine and all these different constraints using in the practical. But overall, it's a very big very big integer programming problem. And here we use the QUBO, try to kind of transfer this constraint into this the second term on the first equation, so that okay we can calculate. And here is the overall algorithm, and this one is already published in the math, okay, last year. And here we show some kind of result, and so basically, okay, and if we have this kind of matrix size is greater, and then we can find this kind of find this, and then by using this kind of for QPU, okay, we can solve this kind of solution in so basically, okay, in this sense, okay, if your size is not big enough with a currently existing kind of solution, it can solve the problem. Much quicker than this kind of CPU time, and also you can achieve this kind of success rate almost 100%. However, if your size becomes larger, then the existing kind of quantum computing bit is not sufficient to describe the whole system. Then in this case, your success rate will drop. Okay, so basically here the results show you that, okay, with the current number of bits available for quantum annealing, it still is limited to a certain dimension. Okay, but no matter how, it's much faster than this classical computer. Okay. Okay, and then the second kind of example is feature selection for machine learning. And then for the machine learning, we have the classic learning facing the complex task. And quantum computing, we can kind of search for all the places. And then how about we do this kind of quantum machine learning, which can fast to do that. And for machine learning, for example, you have to explore, like the reinforcement learning, you have to explore all the different combinations before you can tell that, okay, which one is better, which one is worse. And this is a classical computer, right? And for example, for AlphaGo, okay, they have to explore all these different combinations and to tell the difference. And even though they try to simplify it a lot. And However, for quantum computing, okay, they can try to kind of, they have, for the different state, they can when it's only at some point, okay, they can get the optimal solution. So they can handle much bigger data. Okay, so here on the machine learning, we try to talk about the one specific problem, which is feature selection. So with feature selection, we can optimize the model in many ways. However, for classical machine learning, they have a huge data to train, and relevant feature, irrelevant feature, redundant feature, and also try to prevent outfitting, and sometimes it's not accurate. And also we want to reduce the training time. So basically, okay, then okay, the classical way is set the feature, set the best feature, select the best feature and learning algorithm and evaluate. So basically, okay, for classic feature selection, it takes a long time. And here, okay, we try to quantize this model. So we have the objective function is basically telling this influence, basically, okay, the influence, we have the decision variable X, and then basically telling this, okay, this K is the number of a feature, A is alpha is a bias, and then this the second term is basically the influence, and the first term is basically interference. And here we have this many different constraints for that. And then, okay, for the constraint, okay, and if the constraint is look like the left-hand side, that means these two constraints have some conflict. So basically, okay, we don't want these two features to show together. On the other hand, if we have the constraint on the right-hand side, we want this kind of, to have to rely on each other for this case. Okay. Okay. And then, okay, we try to have this kind of algorithm, and we have the data processing, we have a feature analysis and update the algorithm, optimize this one. And here, okay, in order for this kind of classical computer, we have to explore all this combination to tell, okay, all these things, whether or not I should trust this kind of neighbors interference influence or not. And then this combination is huge, okay, with the number of users increase, it's exponentially go up. However, by using the quantum computing, we can use the quantum annealing so that with a limited bit, we can find this feature selection. And on the right-hand side, we show the number of features with this accuracy. And we can show that, okay, with the quantum QUBO quantum one, compared with the classical method, and okay, we can have a higher kind of accuracy with the classical compared with the other classical algorithm. Okay, and finally, we have this kind of cable routing problem in solar power plant. And basically the story that, okay, we have solar power, and then we try to collect the energy back to this one. And we try to, and the objective is try to, the fast arrangement of minimum building cost is one of the objectives for this solar plant. And then we try to explore the edge of quantum annealing for the network problem. So we have solar power, we have the PV combination box, and the solar converter, then finally go to the grid. However, how to connect them is basically, okay, a combination problem. So here, okay, we show you that, okay, for this node 0, basically this is a solar collection part. And for the different node, okay, this is a corresponding place. And then how could we construct such a tree, such that, okay, the energy, when it converge back to the node 0, the cost will be minimized. And on the right-hand side, okay, we have this pure integral programming, try to quantify this this kind of, constraint for that. And obviously this is can be solved by QUBO. And here we show you this result. And you can see that, okay, this right curve is an original problem that kind of, with such kind of shape, okay? And on this kind of blue column, we try to utilize this quantum computing to fit the curve. Okay, and after that, okay, we can do this kind of, quantum sampling, and then we get the optimal solution. So in this case, okay, we show that, okay, this the solution converges very quick, and then we can get a good solution for this. So overall, the conclusion is like this one. For quantum computing, we have 3 different types: universal quantum, analog quantum, and quantum annealing. Universal quantum can have solve most, all the problems, okay, faced by the quantum, but the number of bits is very limited. Well, on the other hand, for quantum annealing, it's only targeted for a specific annealing problem, but the number of bits is big, okay? And we utilize this QUBO kind of QUBO model proposed by this D-wave, and also we try to combine with the bundle decomposition so that it can solve the mixed integral programming. And after that, we try to solve this wireless network, machine learning, and smart grid problem. And then, okay, recently they have the movie, this Dr. Strange. So you can think about the quantum computing like Dr. Strange. So basically, they try to enumerate all these different kind of situation. And then, okay, after at the sampling point, they can select this right one. And if you have seen this Avenger 4, okay, among all these combination, they select the right one. And he probably have to use the quantum computing to enumerate all the possibilities for this. Okay, finally, here's the reference. And also, thank you for attending. And I hope that, okay, in the future, okay, you can visit our lab. Okay, thank you very much.